Okay, thank you very much, sir, for the invitation. So, unfortunately, I could not join you physically there, but thanks to the COVID system who introduced such kind of things, now everybody from all over the world can be linked through these kind of things. So, uh, about my this presentation today. So, today I'm going to discuss about the scope and potential of energy materials, which is very have a wide application and wide area. But here I will try to give overview of some potential energy materials for different energy application, but more focus will be on fuel cell technology because most of our work is belongs to the fuel cell. And furthermore, the objective of our research is to explore some innovative materials which required for the transition to a sustainable energy system for any kind of sustainable energy application. So here is just contents, like I mentioned, overview about energy, and then about the clean energy, and what is the relation between energy and environment and climate change, and why we need the clean energy, and what is so important in the clean energy, like energy materials. And then I will describe some kind of our experimental results, and then I will conclude at the end of my presentation. So before going to start some kind of about energy materials, I always mention about the energy and environmental relation. If you have a clean energy, then of course you can get a clean environment. You can overcome the environmental issues as well. As you know, the due to the climate change, the situation is going to worse, and its temperature is increasing globally. But we have to focus on these things, and all over the world, people they are focusing on clean energy devices. But meanwhile, what we already have existing system based is on the fossil fuels. But problem is there in fossil fuels, the greenhouse gases emission, like CO2 emission. So as you know, mean in European, they have a plan how to decrease these CO2 emission, and they are going towards the negative emission. And towards the negative emission, actually, we have to first things to actually capture the CO2 emission as well as the CO2 emission as well as the mean how can you capture the CO2 and how can you separate these things. So what will happen when there is more CO2 emission? As you know, due to these fossil fuels, the environment will be more polluted, and the global warming will be increased as what happens nowadays. As you know, I just want to show this figure. I mean, if you can see from here, I mean, in last 100 years, almost 1.5 to 2 degree is increased globally. So maybe one of the climate expert has also established a global warming clock, where you can see the changing of CO2 emission on every second. I mean, how much emission is going on all over the world, and also you can also mean see in particular region and all over the world as well. But he also predicted that, mean what happened in last 100 year, it is going to happen in next 10 years. I mean, like 1 to 2 degree can be increased if this situation can be continued, like the more and more emission all over the world. So that's why it is more important to think about this, how can we control the CO2 emission, and how it can be reduced. So in VN 2050 of the European Commission, they have mentioned how can it be reduced. They have set the plan in Paris Agreement, mean almost till 2050, there should be a zero emission. But some countries has agreed upon that they should go for the negative emission. Like I recently completed one project in the Shalmar University regarding this negative emission strategy. And you can see from this overview, Sweden has achieved negative emission strategy, mean what they are going to achieve in 2030, but till 2021, they have achieved almost their 60 to 70% objectives, and they are already on zero emission, but they have planned for the negative emission. I'm just discussing negative emission. What is negative emission? Actually, negative emission is that in your area, mean in our area, what we are going to emit, mean in the form of CO2, and how much you are going to capture. Mean if you are going to capture more than emission, then it is negative emission. If you are capturing similar, like I mean what you are going to emit, and then you can capture same, then it is called the zero emission. So all these things based on the energy technologies, and in energy technologies, actually energy material is very very important. So there are a lot of things and in this my talk also, it has been divided into two parts. One part is about the existing things, mean based on the fossil fuel, and how can we reduce the emission. And other thing is about the clean energy devices, and for the clean energy devices can be used, and in those technologies, energy materials like in a battery, supercapacitor, hydrogen fuel cell technologies, and in fossil fuel based like a chemical looping system. uh, and they have, I mean, in chemical looping system, we have to introduce different kind of innovative materials. So in first part, I'm going to discuss about the energy materials for the fuel cells. But in fuel cell, what is so important? Actually, fuel cell is based on the hydrogen energy, and hydrogen energy is, you know, is a totally clean based fuel. I mean, there is no any carbon based things in this fuel. So it have a lot of advantages, like it have a high energy density, 142 megajoule per kilogram, and it can be generated from all kind of renewable energy resources. So I mean, there is no any harm, there is no any chance to reduce these resources, because it is the those are the natural resources, and there is no any carbon emission, and it is totally clean energy. So this is some kind of some uh, uh, for students, mean if there is a some people, otherwise I can skip this. So what is fuel cell? Just I will give you short introduction, then we will move towards the our own research part and result discussion. So what is fuel cell? Actually, fuel cell can convert chemical energy into electrical energy with high efficiency, but there is no emission if you are going to use hydrogen. But if you are going to use other hydrocarbon fuels, but there will be less emission as compared to the conventional system. So here, I mean, hydrogen comes from on one side, I mean, from any source as a fuel. On anode, there is a oxidation process, and on cathode, there is a reduction process when you are going to provide the oxygen. But oxygen, mean instead of oxygen, we can use directly air from the atmosphere in this fuel cell. So out, I mean, byproduct is water, and you can get what I mean is a electricity power from the system. So based on the fuel cell, there are different types of fuel cell. We call the fuel cell families based on their electrolytic system. I mean, if there is a different electrolyte, then its name is different. I mean, if it is a proton exchange, mean proton conducting membrane, then it is called the PEM fuel cell, proton exchange. If it is alkaline based, then alkaline, then phosphoric acid based, then phosphoric. Similarly, like molten carbonate and solid oxide. So mean different countries have a different policy. I have overview here. UK hydrogen economy in 2030. I mean, in different strategies to reduce the emission. One of the thing is that to reduce the vehicles on the road from fossil fuels to the fuel cell based or electric vehicles. So they have a plan till 2030. Millions cars, auto vehicles will be on the road, and based on that they are also going to establish different kind of hydrogen station as well. So biofuel cell means, if we can see here the comparison of the fuel cell with uh, other power technologies in respect of the electrical efficiency. Electrical efficiency is much higher as compared to other like fuel cell in this route. But among the fuel cell, as I mentioned, different types, solid oxide fuel cell have a higher efficiency because it is working at high temperature, and also its waste heat can be utilized for further harvesting the energy. As one of the Canadian professor in this field, he is a very famous Brian Cook. He mentioned actually that 19th century was the century of the steam engine and 20th century was the century of the combustion engine. But this century is the century of the hydrogen economy, hydrogen based clean energy technologies, particular the fuel cell technologies. So as I mentioned, in SOFC, as it have a higher efficiency, so every technology have a lot of have advantages, but based on that they have also different kind of challenges. So if you are going to prepare the solid oxide fuel cell, in anode, cathode and electrolyte, it have three components like other energy storage devices, but this is the energy conversion device. And this the main limitation is that it is working at very high temperature from 900 to 1000 degree. So due to that, its other accessories like interconnectors and other things have a high cost, very high cost. So that's why the major challenge is how to reduce its operating temperature. So let's say people, researcher in this area, they have agreed upon that if we can succeed from 300 to 600 degree, then its price can be can be reduced almost more than 50%. So when going to decrease its operating temperature, some materials have a challenges like it's increase the ohmic losses. Some materials are activated at very high temperatures. You can get in more conducting at high temperature, but when you are going to decrease its operating temperature, its ohmic resistance is increased, then its overall performance can be affected and its efficiency can be decreased. So that's why there is need to find some those kind of material which can operate at low temperature. Here just have a comparison of different conventional electrolyte materials. Actually, anode, electrolyte and cathode. Electrolyte is a key component. If you can succeed to get a good electrolyte which can operate at low temperature with a good conductivity, then you can prepare compatible electrodes. So first you have to think about the electrolyte material. So in this electrolytes yttrious stabilizer zirconia is a very common and now it's commercial, but again it is working at high temperature. So every material have their own benchmark and required parameters. So for electrolyte SOFC there is a benchmark to get 0.1 Siemens per centimeter as the ionic conductivity. If same ionic conductivity we can achieve at low temperature, so it would be very good and very nice. So that's why there is a challenge to get a low temperature based material. There is need to develop some materials at this temperature. So there was one European project. I was the one of part of that project that time. So about the nanocomposite for fuel cell. And that project provided the different solutions, but one of the big potential solution for that, how can we prepare that material? First thing, interfacial type of material can be designed where interfaces and interfacial superionic conductor can be designed. Then you can introduce hybrid ion conductors. Mostly in SOFC, solid oxide fuel cell, oxygen ion conductor are more important, are more is common materials can be used as a oxygen ion conductor. But if we can introduce a hybrid ion conductor, its ionic conductivity can be further enhanced. So some materials they are not functional. So if it can be activated, functionalized at the required temperature, can be also good. So it has been divided in these 5 parts. And then of course interfacial redox is also very important when you are going to use compatible electrodes. These are the some great potential for that particular project. In that project, if we can compare C, by C, as I mentioned, yttrious stabilizer zirconia, can get a ionic conductivity at 1000 degree, but after doped cerium material, it can be reduced till 700 degree. But using this technology, using nanocoffs, mean it can be achieved 0.1 Siemens per centimeter at very, very low temperature as compared to this conventional electrolyte material. So another thing is to introduce nano composite, mean nano can enhance the stability and composite can enhance the conductivity of that material. Using these techniques, we started from this electrolytic material, and we prepared a ceria carbonate. Mean first host material was the ceria, doped ceria, mean gadolinium doped ceria and samarium doped ceria, then coated with it different carbonates. And you can see from this electronic image, mean TEM image, where is the here is the carbonated, and inside is the doped ceria. So there is a interface. Actually, this interface can enhance the ionic conductivity of the material. Mean ions can pass through this way. So this is also we give the name as a highway for the ionic conductors, ionic to transport the ions from this path. So after developing this material, it can be seen that the conductivity of the pure SDC, mean doped cerium material, have low ionic conductivity at 300 to 600 degree, but after coating the this carbonate at the SDC, it has suddenly increased at this particular from 300 to 600 degrees. Ionic conductivity is increased. So we have published some similar work in different journals. Then if you succeeded to prepare some good electrolyte, then you have to go for the compatible electrode. Sometimes some electrodes are very good, mean anode and cathode material, but they are not compatible to the electrolyte. Then there is again chances of different ohmic losses as well as the overall polarization losses. So after introducing that electrolyte material, we first go some theoretical calculation using the DFT, and we have seen that the doping of some zinc in the nickel, almost 3%. The is conductivity, electronic conductivity is increased. Actually, in electrolyte there is a need ionic conductivity, but in anode and cathode there is need electronic conductivity, and it has been tested in fuel cell. And if you can see in previous the power density was around 800 milliwatt, but here after introducing this compatible electrodes, is power density is increased from 800 to 1200, see more than 1 watt, 1 watt per centimeter square. So another work regarding that from this nanocoffs, one of my PhD students, she actually developed one more material, but she has seen that co-doping effect. Before was Marian doped CDR, but after that we have introduced the co-dope as a strontium, and there is again coated with the carbonate, and you can see from this TEM image, and there is a SEM image, there is this like a core shell. So it can be animated like this, and it can be seen like this way. Ions can pass through these interfaces, and its ionic conductivity is again increased from lower to high temperature. And we have prepared different composition, and based on that, we have also studied some electrochemical impedance spectroscopy, and you can see perfect semicircle, like exact semicircle, which gives the confirmation for the ionic behavior of the material in the electrolyte. So, but here is, you can see when there is a composite and its semicircle is some more increase, and conductivity, resistivity is decreased and conductivity is also increased, and we publish in different journal. Another work, because there is a different materials, you can explore different things and different, but you have some benchmark and different parameters. So after that, another my PhD student, he has studied different alkaline earth metals as a co-dopant in the Syria, and found different behavior. It have a more stable, and the conductivity is also increased, And here are a few results: barium based and calcium and some strontium based. Mean they have a different, and you can see barium have a better performance mean at low temperature functions. And also mean in this way mean cell impedance spectroscopy mean ionic behavior is there, and there is a spot spikes there, which is also confirmation of the some electronic behavior in that particular material. After that, I mean that was about the conventional SOFC, which have a three layers: anode, electrolyte, and cathode. Another thing, as I mentioned, when there is a three layer, there is chances for the polarization losses and ohmic losses as well. But if you can reduce these different kind of components, I mean from anode, electrolyte, cathode, actually we introduce one composite material which can give you three kind of properties as a anode, as electrolyte, and as a cathode. Actually, it have a almost mixed ionic conductor, I mean mixed ionic and electronic conductor, both behavior. It has ionic conductivity as well as electronic conductivity because it's a composite of both kind of conductors. So it have a same advantages like other SOFC, and means you can use hydrogen as a fuel and also other hydrocarbon like ethanol, methanol, biogas, and natural gas, and as well as the coal-based, carbon-based as a fuel. So in this, when we see mean this composite material, we prepared in a single layer, mean in single one step, and we tested it. If you can consider like a one page have a two side, one is left side, other is the right side. So there is actually one side can work uh, as a can say as a node, and other side can work as a cathode. But in between there is, we can see there is some virtually layer which can work as a electrolyte. So based on that, we have published different on this particular single layer fuel cell. And when we submitted nanotechnology, they suggested fuel cell 3-in-1, mean from three to single layer. In this way, mean material cost can be reduced and its prices can be reduced, and further different things can be mean overall in different aspects, geometry and overall it smart device can be produced from that particular things. So here is the working principle of that. You can see here is the red and gray kind of balls. Actually red is the electronic conductors, and these light blue or gray, you can see is the ionic conductor. So it's a mixture of that. When hydrogen is there, it's like a p-n junction diode. I mean, when you are applying it potential there, there is a one. I mean, in between NP junction, then there is a create some depletion layer, and electron can pass through the outer circuit. So similarly, like that way, hydrogen when is here, there is a nanoredox level per particle to particle from ionic conductor to electronic conductor. In this way, when hydrogen is there, then like TPB three-phase boundary, there is a electrochemical oxidation process, and electron can pass through when you have applied a load, and electron can pass through this, and there is a virtually ionic conductor. I mean, on one side electron and other side the electronic conductor, and in between ionic conductor can be make a depletion layer, so which can prevent the electronic and short circuiting of the electrolyte. Based on that, further different mechanism has been studied in our groups, and then Schottky junction effect has been studied, and we published an advanced energy material. And then one of my MS student recently, she has done this work tailoring the ions and band gap in a novel semi-ionic energy conversion device for electrochemical performance. Actually, concept was proved, but have to optimize further. Either there is the effect of the band gap, and also there is effect of ionic and electronic equilibrium. I mean, how much ion conducting should be there, how much the electronic conducting should be there. So actually in this way, we actually use the semiconductor material and ionic conductor materials. Based on that composite material, we prepared one device and tested that. And here you can see One is the based on same material, we tested in conventional and tested in the single layer. And single layer have a better performance as compared to the this one. So then we have optimized and we have seen at SiAC4 when there is a 60 and 40 ionic and electronic combination, 60% and 40%, then there is some good performance. So there is further different projects going on, how to study the topological ionic behavior in that materials, and we are exploring different kind of transition metal oxide, perovskite, and heterostructure. Different projects are going on. So just want to show some activities. We have some good collaboration with the Sweden, and last time one of the Swedish ambassador visited COMSATS, and Professor Anis knows about that one. And then they join hands, and based on that one, we applied one project with the Sweden, and it's called the SIDA, Swedish International Development Cooperation Agency in Sweden there. And with the Professor Mikhail, I visited there in Linköping University based on that project, and we further agreed upon these kind of things on Sweden side. Actually, project things were that how can we explore new energy material, and Sweden will be focused on how to enhance and scale up the material, and can start up different kind of things. And but our focus was on the energy materials. Another thing is, I think I could not explain everything here, but thing is that one of our proposal we submitted about the with China and Pakistan about the economics corridor. We gave the name, why not should be it is a knowledge corridor, and we submitted one proposal,
Dr.
how
Rizwan.
can uplift the socio-economic condition of Pakistan. So, and based on that, we submitted also project with the different universities, and recently we awarded one project with the one Chinese university regarding this one. And here is another one of actually based on that collaboration from Sweden. We recently
Dr.
published an
Rizwan,
AC
please
energy
wind up.
material. One
The
slide.
time is almost and you have 2 minutes to wind up, please.
Okay, just I'm going to finish everything. But and this actually just a new idea. I want to just little bit give about this. Uh, Linköping University, I visited there, and they have some good silicon carbide, and we use that silicon carbide and impregnated. We use our own anode material, lithium nickel oxide, and then we tested in a ethanol-based fuel cell. There is need some good catalyst, so it works very well. For that hydrocarbon fuels, silicon carbide and lithium nickel oxide based material, and it gives some reasonable. So further, another project based on, we have seen different kind of waste material from animal waste, lignite, redwoods, agriculture waste based material, and based on from that those agriculture waste, what kind of biogas can be achieved, and those biogas can be used in a fuel cell. And we develop a one model. Our undergrad student have developed this model, and we publish in it. Another thing is project about the recycling of UPS waste batteries. Project one of my PhD student with the GC University is working, and here is a catalyst about natural gas. And about this, I just going to finish after that one. So we as you know, every person have a breakfast, and most of the people using eggs, like in the form of omelette or in the form of other things, boiled eggs. But eggshells mostly is going to waste. In some countries they are using for the biogas, but as I mentioned, electrolyte for the fuel cell is more important. In fuel cell, electrolyte have a rare earth materials, and rare earth are very expensive. But some of our undergrad students, they get calcium carbonate extracted from these waste eggshells, and we use that calcium carbonate as a dopant in the cerium, and we develop the electrolyte, and those that electrolyte works very well, and it gives some good performance. Another thing, same electrolyte with some Portuguese professor, they have used our material, and it has been used for the CO2 separation. I'm going to skip this chemical looping system. So just at the end, Rise. Thank you very much, Professor, and invitation. Actually, I have skipped my recent work about the chemical looping based system where we can use only CO2 capturing and CO2 separation actually from the existing power plants in a fuel reactor and a reactor. And there is use some oxygen carrier material, and we develop some oxygen carrier material, and it can be used for the separation of CO2. So in our lab, I mean, our focus is on the energy material. That is our research group. We have a good collaboration with China, even also with the Turkey. There is in Istanbul Technical University. There is a one professor, Professor Salma, and another university. We have submitted last time one project with them. So hopefully from this platform, this conference, we will get some good collaboration, and in future we can submit some Tobitech and Pakistan funding agency some good projects as well. Here are some collaborators, and thank you very much. Let's save the word together. One of my students have developed this theme and this figure to focus our overall objective of our research group. Thank you very much, all of you.
Thank you very much. Thank you for the very informative talk. So we can have one or two very quick questions. I just ask one small question as we have already running out of the time. You
Yes.
said that the internal ohmic losses, they are quite effective or of no use when we increase the temperature. How you can measure these internal ohmic losses, or how you can minimize these?
Actually, yes, it's a good question. So, of course, it's the main challenge of such kind of materials. And if I can say, I mean, overall polarization losses, three parts: activation losses and ohmic losses and the mass concentration losses. Actually, activation losses is based on the material overall, I mean, based on open circuit voltage, but the mass concentration based on the fuel. But ohmic loss is actually based on the conductivity of the material. If the material have a good conductivity at particular temperature, I mean, if I can say the conductivity in both way, ionic or electronic. If you are going to prepare the electrolyte, then we have to think about the ionic resistance. But if you're going for the anode like nickel oxide base or zinc oxide base, then you have to improve its conductivity. That conductivity can be improved in a different, there are different way. I mean, you can introduce some nanoparticles at the nanoscale. Its conductivity can be use
Okay.
that those material in a cell. There is interface. Actually, those interface have a very important role to overcome the ohmic losses. If there is a more compatibility, like a if I can say the uh, thermal coefficient. If they have a compatible thermal coefficients, then interfaces based ohmic losses can be also reduced.
Okay. Okay.
So there are
Thank you, doctor.
more parameters.
Once again, we thank you, and your certificate is with us. Thank you once again.
Yeah, thank you very much, sir.